So hey guys, welcome back to my channel. Hope you're doing extremely well. And today the GFG has brought to us a good problem. I say it's a hard type problem. It is possible paths in a tree, right? Okay, so we will be solving this problem today. Okay, so possible paths in a tree. So what has been given is you have been given a tree in a form of this, a vector of vector, right? So this is my one node. You can see one. Second node, two. And this is the weight corresponding to 1 and 2. So 1 and 2 is connected by an edge whose weight is 1. That is the weighted component, right? Then another node is 2, that is 2. 3, that is 3. And 4, that is this edge weight is 4. So this is the graph given to us. This is the input graph given to us. Now, the question says that you have been provided with an input list, okay, which is the query list, which is the query list. All right. Now, in this query list, what you have to do is, let me yeah. In this query list, what you have to do is, suppose the query list says that the first query is 1. First query is 1, that means, let me change the thickness here. First query is 1, that means you have to provide me the number of paths from any node to any node, let's say from A to B, right? From any node to any node, such that the sum of this path is less than query weight, that is 1. Okay. Now for 1, you can see that only one path exists, that is 1 to 2, that is less than 1, less than equals to 1, sorry, right? Now for 2, you can see again only 1 to 2 is the path, you can say. So 1 to 2 is the path, right? For 3, you can see again 1 to 2 is the correct path only. For 4, you can see now two paths are available, 1 to 2 and 2 to 3. So you will say answer is 2, right? For 5 now. So for 5, there are three paths available, either 1 to 2, either 2 to 3, either 1 to 3. So your path number is 5. Your path number is 5. Okay, so this is one here, this is one here. Again, one thing is also given that consider A to B and B2 is same, that is not double count. You can see the 2 to 1 is also 1, but don't double count, consider them as 1 only, right? Okay, so this is the problem statement given to you. You have to provide me the answer as 1 1 1 2 5 2 3, sorry, this is 3. You can see above 3. All right, so this is my answer vector. Okay, now I think you are clear with the input and output scheme, and now you want to see the what do we say, approach, right? So as usual, we will talking about brute force approach, and today's brute force approach is also a medium type problem, right? So it is that type hard question, right? Okay, so brute force approach says that you want the path, okay, we want the path. Now, is it a tree or a graph? Does this look like a tree to you? I would say no, because the edges are undirected, right? And 3 could have also connected to 1, right? This is not a tree. I will treat it as a graph. So first conclusion is this is a graph. Second thing, whenever we are in graph, what do we have to do? Either we have to go for a BFS or to go for a DFS. That is the approach, right? In 99.9% problem. So we will test that. Either we have to go for the BFS or for the DFS. Which of these traversals will work here? Now, what does BFS give us? BFS means breadth first search, so it give us levels. And DFS is depth first search, so it give us paths. And we discussed above we need paths, so we will be going with DFS. So what we will be doing is, for each query, for each query, we will run a DFS from each node. For each query, we will run a DFS from each node. And then whenever during the during DFS of a node, if path sum, we will be requiring a path sum variable and we will be updating it regularly basis. If path sum exceeds our query value, let's say query value is x, exceeds x, we stop, and then just add the add the number of the paths encountered up till now into the sum, right, into the answer for that query, and then move to the next query, right? Okay, this is my approach till now, right? So how will we be able to implement it? So the first step for implementing it will be, for a successful DFS, I will be making a adjacency list, because I have not been provided with the adjacency list. I have been provided with a somewhat of a matrix, not matrix also. I have been provided with the two endpoints with the weight, right? This is not an adjacency list, so I will create an adjacency list first of all, right? Of like, and I will treat it as a undirected graph, and then I will create it, right? Undirected graph. My second will be DFS traversal for each query. I don't think that I need to elaborate on DFS traversal. You are pretty smart enough to handle that. So DFS traversal for each query. And number three is counting paths. Counting paths. So what do I mean by counting paths? Then while traversing to the tree using DFS, if the maximum edge width encounter is less than or equal to the query, we continue exploring further. But if the maximum edge weight exceeds the query value, that is exceeds the query value, it is greater than x. In that case, we stop further exploration from that node and this update the result, right, and move to the next node. Now, counting paths and update results. Fourth is updating result also. We have to update the result also, right? Update result. That is, we count the number of paths encountered during DFS, where the maximum edge weight is within x, and now this count is updated each for each query separately, and then we will return results. We will return the vector of int we encounter we made, sorry, vector of int answer we made, right? So I don't, as usual, I will not be coding the brute force approach, but I will be discussing the time complexity and space complexity from with you. So the time complexity will be, any guesses? The time complexity of this will be divided into three parts. First, we had to build an adjacency list, right? We had to build an adjacency list. So O of n for it, right? Now we have to perform DFS for each query. DFS for each query. So there were q number of queries, for example, and now for each query, what we were doing is each DFS traversal takes O of n time. We know about that. And now, since we are performing DFS for each query, and each DFS traversal takes O of n time, the total time complexity becomes O of q into n. O of q into n, right? So our answer will be, it will be n plus q of n. So it will be, I guess it will be going into q of n only, right? Because q plus 1 n then will be treated as qn only. Okay, O of qn. But is the space complexity? Now we have made an adjacency list extra, so it will be O of n times, so O of n space for adjacency list, and additional space for DFS traversal to maintain O of n visited array. If you remember, while doing a DFS traversal, we have to maintain a visited array so as to not visit the components we have already visited, right? Because we have to treat A to B and B to A as singular path, so we will be using a visited array also, and normal DFS also takes BFS traversal. Oh, normal DFS traversal also takes visited array, right? So I hope you're clear with this up till now. If you find it difficult, please watch it again, because the next part I'm going to tell you that the optimized approach is really difficult. Not difficult, I will say. It is very conceptual. You will have to know the concept of disjoint sets. Disjoint sets. See, there are multiple videos present on YouTube from where you can learn about disjoint sets, but still, I will try to help you in learning it. So I will go to the GFG section of disjoint set, right? Okay, and I will read it out for you. Now, it says, what is set data structure? It said the two sets are called disjoint sets if they don't have any element in common. The intersection of sets is a null set. That is a set. Suppose first set is 1, 2, and second set is 2, 3. Is it a disjoint set? No, because 2 is a common element in both of them, right? But 1, 2 with 3, 4, it is a disjoint set because they don't have any common, right? The intersection should be null. Okay. A data structure that stores non-overlapping or disjoint subset of elements is called a disjoint set data structure. Clear? The disjoint set data structure supports following operations. What? Adding new sets to disjoint set. Okay. Merging disjoint sets to single disjoint set using union operation, right? So we can merge different disjoint set. We can merge we can merge these two, 1 2 and 3 4, if there is a connection between them, if we want them to connect, right? Finding representative of a disjoint set using find, like I want to keep a parent, that how, from where these sets originate, like what I'm saying is, so if I merge them it becomes 1 2 3 4, but I want to keep it that this 1 2 3 4 came from 1 2, and this 1 2 in turn came from 1 which was merged with 2, right? So this is my parent for 1 2, this is my parent for 1 2 1 2 3 4, right? So this is something like finding representative, the representative as in parent. And then we can also check if two sets are disjoint or not. Now you can read it from here, I will provide the link in the description also. And then why are we using disjoint set? So in DFS what we were doing is, DFS is used to find that whether the nodes we are talking about are connected or not. Nodes we are talking about are connected or not. Connected as in, suppose this is my graph, 1 connected to 2, 2 connected to 3, now 4 connected to 5, right? And I say, and I raise a query, are 1 and 5 connected? From this graph you can see visually, but if you're not given the graph, you're given the address list, you will have to run the DFS traversal. Now what will the DFS traversal do to you? It will start traversal from here, traverse this, no means to go here, right? Return back, then start traversal from here, traverse this, right? You will see that the traversal technique, that the 5 didn't occur in the traversal of 1, right? 5 didn't occur in the traversal of 1, and then you can say that 1 and 5 are not connected, right? 1 and 5 are not connected. So what is the time complexity that took you? It took you O of n time, right? You have to traverse of all the nodes, right? Disjoint data structure comes as a, what do we say, as a helper, and says that no worries, I am here. I will be providing with yes or no in O of one time complexity, a constant time complexity. As it says, you ask me, are 1 and 5 connected? I will say no. Are 1 and 3 connected? I will say yes. Are 1 and 2 connected? I will say yes. Are 1 and 4 connected? I will say no. Right? So this is the functioning of disjoint data structure, right? Disjoint set data structure. Okay. Now you can read from this, about disjoint data structure from here, and trust me, if you don't know about it, please read it, then watch my video further, right? Okay. Now, what is our view here? What is our implementation? What is our approach here? So my approach is the code use the concept of disjoint set union. As I said about union above, that the same only. Disjoint set union. Why disjoint set union? To merge the sets and calculate size of the merging set. Size of the merge set, right? But the key intuition, our intuition is to sort the edges according to the weight, according to edge weight, right? According to the edge weight, and then maintaining them in an ascending order with their endpoints obviously, and then perform the union operation on the edges sequentially. Perform union on the sorted edges sequentially, right? Now, by keeping track of the maximum weight of the connected components after each union operation, we can efficiently find the maximum weight for each query. What we are doing is we will keep track of the maximum weight of the connected components, right? So suppose I have formed this as one connected component, this as another connected component, this as another connected component. What do I mean by connected component? As in this example, the disjoint set union will form connected components. So first connected component will be forming 1, 2, 3, and other will be forming 4, 5. So this is my one connected component. This is my another connected component. So okay, so I will form connected component, right? And I will say that this has all the answers below or less than 6. This has below the all the answers below less than equals to 8, 9, right? So if I want a query with 7, if I want the query with 7, so what will I say? This size is okay, and this size is not okay, this size is not okay. So answer is will be n1 here, right? N1 is the size of this, n2 is this, and 3 is this, right? So n1 will be my answer here, right? Now let us look at the implementation really fast. That is pseudocode etc type of thing, and then we will be moving towards the code. So hope you're liking this video, and if you're new here, don't forget to subscribe, right? Implementation, right? Initialize necessary variables first of all, right? Initialize necessary variables. Create your answer variable to 0, right? Okay. Then create two vectors. I will require two vectors here. One is parent and other is sz, right? This will be of size n plus 1. This will be of size n plus 1. That is the number of nodes plus 1, right? Because the number nodes are ranging from 1 to n, right? So that is why n plus 1 to keep the maximum index as n, right? This will be storing my parent, as you can then name suggest, and this will be storing my size of the disjoint set, right? Now initialize each element is its own parent and set the size to 1. So what is the next step? Initialize each element as its own parent and size as 1. That is in the initial component. All the elements are disjoint sets individually. All the elements are disjoint sets individually, and their sizes are 1 because they are only connected to themselves right now. Now create a vector of pairs, that is pair of int, pair of int int, right? Let us name it as uh, let us name it as wt, right? Okay, this will be my one endpoint, this will be my another endpoint, and this will be my weight, right? So endpoints, this will facilitate my sorting. I will sort it now. I will sort wt, right? This will this will give me wt as sorted version according to the edges weight, right? Now I trade through each edge. I trade through each edge and push its weight and endpoints to WT. And push its weight and endpoints to WT and then sort it, right? That is done. Now, create a map. Let us create a map and let us name it as MP. What with this map store is the map will store the maximum weight. Map will store the maximum weight of the connected component with weights less than or equal to each query. Maximum weight of the connected component with weights less than, because the query required less than or equal to, right? So less than or equal to each query. Okay, so this is my first step. My second step will be to perform union operation and update the MP. Perform union and update MP. So you can read about union from here. You will be finding union here. So you can see union here. You have to read union up till the last. That is the homework from my side. Please, please, please study about union and find. Okay. And if not possible, if not able to understand what is saying in theory, there are multiple videos present on YouTube. Please take some time out because the connect today's question is really important. Really important means a very good question conceptually, right? Perform union and update MP, right? What we are doing is iterate through sorted edges. That is WT, right? Sorted edges, right? And then extract the weight. We have the weight. We have the first endpoint. We have the second endpoint. Okay, and use union function to perform the union operation on the endpoints and update MP with maximum weight of the connected components after each operation, right? Then use the union operation on the endpoints on these endpoints, and then update MP your map with maximum weight of the connected component after each operation. So what we are doing is, see, I know that you are confused up till now. So what we are doing is, you have a connected component, you have a connected component, multiple connected components stored in a map, right? Okay. So suppose this contains 1 to 2, 1, 2, and 3, right? This contains, let's say, 4, 5 up till now. This contains, let's say, 6, 7, right? Okay. Now you get a edge 3, 4, right? And the weight is 1, right? Okay. So this map contains all the edges up till 5 sum, 6 sum, 7 sum, 3 to 4. This component is being connected to this component with the edge weight of 1, right? So I can form a set and update the MP to contain 1, 2, 3, 4, 5, and the edge weight will be 5 to 6 plus 1, that is 13. Correct? Correct? So this is my one other connected component. So I'm updating my MP to store this, right? Now process each query, create a vector result to show the results of the each query, and iterate through each query, find the element in MP that is just greater than query using the upper bound function. We'll be using upper bound function here, and then I have created my result vector here, okay? And then if there is no such element, then append 0 to it, and if otherwise, decrement the value and append the maximum weight. Okay, append the maximum weight value from the map. Okay, and return the result. That is for sure you must have understood. Now, what is the time complexity and space complexity that we'll be discussing about after the coding area, right? After the coding area. So let's move to the code now without wasting any time. Okay. So I was not able to make a video with dynamic coding in front of you. Sorry for that because I had to head somewhere and I don't have actually time for recording such a long video. But I still have tried to write the code for you with the proper functions, with the proper comments. So I think you will like it. Okay. So I will explain you what is happening is we have created our answer as 0, right? Okay. Okay, this is my weight now. I have created my vector as and size as promised of size n plus 1, and you can see we have now we will assign all the parent as itself and size as 1, right? That is all the disjoint sets are currently each element, right? All the elements are disjoint sets. Now we will get a pair of int vector and store the edge. Edge I2 is the weight, edge I0 is the first endpoint, and edge I1 is the second endpoint, right? We will sort it, already discussed. Now we will create a map to store the maximum weight of the connected component with weights less than or equal to each query, right? Okay. I will be iterating to the sorted edges 0 to n minus 1, right? And then performing the union operation. So A is my first, that is my weight. B is my second, that is my first endpoint. C is my third endpoint. And then we will update using the union operation. So let's see what is the union operation doing. So union is taking A, B, parent and size. Okay. RA, that is the root of A, is the parent of A, right? Root A is the parent of A. So what is root A doing? You can see about root. Root is actually find here. Okay. This is the root operation. So while parent I is not equals to I, then move towards it. That is, suppose my parent is, what is happening is, let me explain you. So suppose uh, 1 connected to 2 connected to 3. Initially the parent contained, let's suppose this is 1, this is 2, this is 3. The parent contained 1, 2, 3. That is, 1 is the parent of 1, 2 is the parent of 2, 3 is the parent of 3. But after updating, it will look something like 1, 1, 1, 1, 2, 3. 1 is the parent of 1, 2, 1 is the parent of 2, 1 is the parent of 3. I'm standing at 3 and I want to know what is the actual parent. And I'm standing at 3, I want to know what is the actual parent. So what will I do? I went to 3, I saw, sorry, just a minute. Yeah. So it is 2 here, right? What is happening is 3's parent is 2. 3's parent is 2. So it will go to 2. It will say, hey 2, are you the parent of yourself? 2 will say, let me check. 2 will say, no, I'm not the parent. 1 is my parent. I went to 1. Hey 1, are you the parent of yourself? 1 will say, yes, I am the boss. I am the parent of myself. So the extreme parent, that the grandfather, etc., is 1. Right? So the tree is starting from 1 and extending up to 2 and 3. Right? Okay, so this is happening. So I am standing at 3 and I want to find the 1. That is the root 1. Okay, so I'm using the find operation. You can study about the find operation on the link provided in the description. So this is a simple implementation of the find. Similarly, I found the root of A, root of B, right? Now, if the roots are same, that is they're already in the same set. If the roots are same, that is 3's ultimate parent is 1, 4's ultimate parent is 1. That means 3 and 4 are already in the same set. 3 and 4 are already in the same set. I don't have to do anything, right? I will just return size of RA into size of RA, right? Okay, after that, otherwise, if size of RA is less than size of RB, that is size of set A is less than size of set B, then we will merge the two, we will swap them. Just for the sake of complexity, we will swap RA and RB, we will swap A and B. Okay, so RA and RB are both swapped now. We will merge the two sets by updating the parent and size. We will merge the two sets by updating the parent and size. So what we are doing is, so suppose 3's parent is 1, 4 parent is 2. They were not connected up till now. They were not connected up till now. But now they are connected because of 3, 4 edge, right? 3, 4 is an edge. So 1, 2, 3, 4 are connected, right? So this size is 5, suppose. This size is 4. So what we are doing is, our new size will be, this size is 5, this size is 4. That means, what do we say? This size is 5, this size is 4. That means that the total size now is 5 plus 4, right? 5 plus 4, that is 9. Right? Now we're making the parent with the more size as the ultimate parent. So like in that case 5. So we are making 1 as the ultimate parent of these also, right? But if some case it is 4 and 5, so to not handle it else case etc., we are just swapping them. So it becomes, it was 1 4 2 5, right? After swapping 1 and 2 and 4 and 5, it becomes 2 5 1 4, right? So I have this value in the on my left only. That is why it becomes easier for me. Okay. We have merging the two sets by updating the parent and size, right? Parent of RB becomes RA, size of RA plus equals to size of RB, right? How we are updating it, how we are updating the size. So as suppose 3's ultimate parent was 1, 4's ultimate parent was 2. So in the index of 2, parent was 2. In the index of 1, parent was 1, right? Now to update it, I will not update these values. These values are ultimately leading me to 2. I will just change it to 1. Now the ultimate parent will become 1, right? Okay, so I think you are able to understand. And then we increase the size by RA into RB, right? And return that. So now this was the working of my union, and then I have got all the answers and I've updated them into the my MP, right? From the weight. Now vector int result. Simple. We will store the result of each query. I will go from 0 to q. Value equals to upper bound of queries. Now there can be two cases. Upper bound returns 0, upper bound returns some value. If we return 0, that means no element is present, no path is present in the answer. So if value equals to mp dot begin, result pushback 0. If there is no such element, then maximum weight is 0. Else, val minus minus, we will store the maximum result, that is val dot second, and store the maximum value of the query, return result. So I hope you liked my answer, or I hope you liked my code. Now discussing the time complexity. Okay, the time complexity of this code is n log n plus q log n. Let me write it here for your sake of better understanding. N log n plus q log n. Reason is complexity is dominated by sorting the edges. So we have to sort the edges first. So this is taking L log n. Now the subsequent union and query operations. So it is working q times, and the union also working log n times. So it is taking q log n time. And the space complexity is O of n because we use a parent and child. Okay, so this is my total complexity here, and I hope you liked the video. If you liked it, don't forget to like it and subscribe to my channel if you're new here. And thank you guys. Let me show you the results. Works fine. Works fine. Submit it and let it run. In the meantime, it will run only if you subscribe the channel. So you can see the pointer going up, and it will give me a 95-day streak. So thank you guys for watching the video. Hope you liked it, and thank you for watching. Bye. Have a nice day.